just in case, just videotape this. So okay, so as you can see now that I can have equality, we already deal with like equality and inequality constraint, and for inequality constraint will be still the same. Like we'll just assume that we can swap this to this min max thing. If we swap that, then I will just have this mean lambda less than 0 if this is an inequality constraint, pull out, and then I try to maximize this over x first. Then again, I will try to do the gradient stuff like that. So then immediately we will have something like the optimum will occur when like the gradient of fx is equal to lambda gradient gx, something like that. Like sometimes like when we first learn Lagrange multiplier, like we will just like go to this directly. And of course there's some very nice like graphical picture to see like why this is supposed to be so. I don't have a visualization here, but I'll just have this kind of algebraic reasoning. It's a little bit easier to explain. And let's see what I have here. And now if I go back to here, if I have the x here, let's say x star is actually the optimum. There's a, the optimum point for this optimization problem. Then if I compare like this side and this side here, I essentially have like, on this side it will be just like, it's just like fx star here, right? And on this right hand side I have like this additional stuff here, but I also have fx stars here, right? So what it means is like I must have like this additional part should be equal to 0, right, at the optimum point. So therefore, like if I have the optimum x star, I should have the corresponding lambda star there, such that this lambda star gx star minus g1 is equal to 0, or g0 actually. Suppose g0 is equal to 0. And this actually have a name for that. This is called, this condition is called like complementary slackness. It's kind of fancy name for that. Including this, and also the gradient things, and also the sign for the Lagrange multiplier. I basically can summarize all these conditions together, and that's what I mentioned. Like, it's called this KKT conditions. This is a conditions to just to list out the optimum point for a kind of constraint optimization with like both equality and inequality constraint. So let's say I have like inequality constraint like gx is less than equal to 0 and hx is equal to 0. Then the KKT conditions for this particular case will include like, so I have this gradient fx minus mu g, gradient gx minus lambda gradient hx is equal to 0. Maybe I should put a star everywhere, but I just skip that. And then of course, I should satisfy the constraint, right? The original constraint. I should have gx is less than or equal to 0, and also the equality constraint hx is equal to 0. And remember, like when we have inequality constraint, then as we explained earlier, that our Lagrange multiplier should not be unbounded, like on both sides. So therefore, like given this, actually earlier we have like the sign is like gx is bigger than or equal to g0, but here if when it's gx is less than or equal to something, then the sign is flipped. Actually, we should have like mu is bigger than or equal to 0. So remember last time mu is less than or equal to 0. And also, like we just mentioned the complementary slackness, where we have this mu gx is equal to 0, something like that. Let's see. I think I didn't have that in my notes, but I think it should also have this lambda hx is equal to 0, right? There's no good reason why I don't have that. So, but anyway, like as I mentioned, yeah. So, you have some questions there?
No, I was just looking at the slides.
Oh, okay, yeah. So, but anyway, like this Cauchy-Tucker condition is like, hey, speaking nice, I think like you can more or less derive that, but this is a pretty significant paper by I guess first actually Cauchy actually made this master thesis, and no one realized that like until for quite some time, and so therefore like in the past people call it the Tucker condition. That I forgot like when they had the paper, but anyway, that basically just like lists out all these conditions for like inequality and equality constraint optimization problem. And I won't go into an example because I will see an example when we talk about this source coding. So any questions for now, or like I would just say move into like compression. So new page. So we're going to talk about source coding. This is I don't know why people just come up with all this name coding, but it's essentially just compression. It's compressing information. But actually I can see why they call it coding. But of course it's not programming. It's just it have some so in the sense that the classic problem that it's trying to deal with is actually Shannon trying to deal with is of course want to mention Shannon. His original problem is think of you have a so-called discrete memoryless source. So it's just basically you have a probabilistic source. This is discrete, and you will keep sample this source. So therefore, this is just a PMF here, a probability mass function. X can take values, for example, for some discrete set here. So maybe x1 up to xn, some discrete values. And then you just keep sampling this thing. And then the question is how much entropy or how much information for this source here. So one way to think of that again is given a source like this, or if I have sampled this source n times, so I have maybe I shouldn't use n again, m times, I have x1 up to xm. Oh, there's some I don't know, there's some maybe I change this to a1 to an. So this is just I sample it m times, and I have a sequence for that. So can I find some way to try to compress that? So this is a encoder into some binary streams. So and maybe I have streams of binary string of k bits. So therefore in this case, if I can do that, then it's essentially compressing this guy to just compressing it into k bits, or there will be 2 to the k symbols there. And of course, if I compress it, if I cannot recover that losslessly, that would be meaningless. Then hopefully this bit stream, if I kind of go through a decoder, it will get back to the original one. So I have x1, xm. So this, maybe I call it hat here. This would be equivalent, something like. So that's the goal here. And the result is let me jump ahead with the result. Result will be I guess I kind of briefly mentioned that last time, is you can think of each time you are going to pull out something off here, right? And the one that is least likely is actually most surprising, and that will contain most information. And the amount of information it turns out will be just log 1 over p xi, let's say, for the symbol I. So whenever I have symbol I there, the amount of information, it turns out, we will elaborate later on, but it turns out that will be just equal to log 1 over pxi. And then again, this happened with probability xi, right? So therefore, if I weighted sum them, then on average, the amount of information from this source will be equal to this guy here, and this basically the entropy. Or in other words, if I have a length M sequence here, I can compress into k bits, right? As I mentioned, k bits, and that k bits will be equal to this multiplied by m. So in the following, we'll just show like why is so basically. So we look into like couple ways. Like first way is like we just look into a constructive or like more lateral way. It's like okay, we indeed we are trying to compress that. So if we're trying to compress it, or like in the sense that this is an encoder, we're trying to code this thing, then I'll create a bit stream like C. Let's say for each of the symbol, I will just replace that with a code for that. So for example, like for x1, I will have a code like cx1, and x2 I have cx2, and so on, and I have xm will be have a code cxm, something like that. And let's say like for each of this code, I have length for this code will be like lx1 bit, and this xm will have like let's say lxm bits, and so on. So therefore, like in this case, after this compression, I will have after the encoder, I will have like say in this case, we'll have like cx1 6m as the output of my encoder, and the total number of bits here or k here is just equal to lx1 plus lx2 and so on up to lxk. So now of course what I want to do is this source is stochastic, right? We just want to make the average as basically if I want to have a good compression, I want to have this average length to be as small as possible. So therefore I want to minimize this average Lx here. So be careful with my notation here. This now x is a random variable, right? Lx will be like again a random variable, right? So on average, right, this expectation Lx is as small as possible. I want this to be small. But of course I have some constraint here, right? The constraint is this compression should be lossless. So after I do, if I just map it into arbitrary things, and then if I cannot decode that, then it would be useless. So now to make sure that this procedure is lossless, so we'll define something called uniquely decodable code. Uniquely decodable. This is just a name, right? Uniquely decodable in the sense of course why we call it uniquely decodable is just think of when it won't be decodable or when we will have lossy problem. It's if we have two symbol or maybe x1 and x2, if they both code into the same thing, if they're equivalent, then of course we cannot recover that. So therefore we're supposed to be uniquely decodable in that sense. But actually this is the worst case. This is the most silly case. If we have x1, if we have some two symbol x1 and x2 and they share the same code, this is totally fault, and we call this a singular code. And but even for non-singular code, that is if we exclude all these bad codes that we just hit on the same code word for like different symbols, we cannot ensure that it's uniquely decodable. I mean, non-singular does not guarantee to be uniquely decodable. Why so? Like, can you see why? There's an example in my slide. Yeah. So let's say A equal to 0. B, I have several symbols here. B map to 1, C 1 0, D 1 1. Right. So okay, this is not a single code, like each of them map to different things, right? But this is not uniquely decodable because if I have, like, for example, message this 1110 here, there's several combination possibility, right? I can either have like it's actually DC, or maybe I have like BBBA, right? So but there's something more than this long single condition for the code to be uniquely decodable. So basically, we want to ensure that, like, logic say, if we have like C, just take two symbols like CX, or like two characters, xi and xj, ensure that cxi is not equal to cxj. But we also consider sequences of characters. So for arbitrary character sequences, when they are different, they cannot share the same code. And or that basically saying that, like, if I have like sequence x1 xn, I may sequence like or maybe I write that way. I have sequence x1 up to xn. I have another sequence like x1 hat or tutor up to xm tutor. There are two different sequences. They are not the same. Then I need to make sure that cx1 xn is also not equal to cx1 tutor xm tutor. Let's say something like that, right? To be uniquely decodable. So this can be quite complicated, right? So to simplify that, we consider a subset of uniquely decodable code. We call it like something called like prefix-free code. So it is called prefix-free in the sense that, let's see, in the sense that, like, the code word for each of the symbol cannot be prefix of another code word of another symbol. So for example, like if I have A mapped to 1, B mapped to 0, 1, and C mapped to 0, 0, 1, and D mapped to 0, 0, 0, 1. So you see that, like, for each of the code word of the symbol, it is not prefix of another one. Like this one cannot be prefix of the other guys, and this cannot be other guy. So this is also called like an instantaneous code. So because I think of another example, like actually I should start with a example that is uniquely decodable but is not prefix free. For example, like if I have like A map to like 1 0, B map to 0 0, C map to 1 1, and D map to 1 1 0. So it's not prefix free because I C is a prefix of this coword of C is a prefix of a coword of D here. So now if I try to map like C B B B, in this case C B B B is like 1 1 0 0 0 0 0 0. Now when we try to decode it, we immediately see some problem because when we try to read the bit stream here one by one bit at a time, when we see 1 1 here, it can be C, but if we see 1 1 0 here, it can be D here. So it depends on like whether it should be either case, like it can be either C or D. Eventually we will be able to decide that if we assume that this is D, like let's say if we're the decoder, we assume this is D instead of supposed to be C, then the next we see 0 0 here is supposed to be B here, and then 0 0 here is supposed to be B here, and then we have 1 0 left behind. We know there must be problem here like at the beginning, so therefore like it cannot be D. Then we go back all the way, so then like it's supposed to be C. So you see like it's still like uniquely decodable. Like it does not. I cannot prove it now actually, but it's uniquely decodable at least in this case. I mean, okay, for this coword here we won't have problem like decode it back. But it's not so-called instantaneous. As you can see, like I can keep the decoder probably need to go with many bits before like it is able to decide like what's the first symbol supposed to be. So and you see that like if I have these prefix free features for your code, then we can pretty sure that like we don't have this problem here, right? We have this problem is basically for this case here, for this code here, is because C and D we cannot distinguish which one is which because C is the essential prefix of the other guys. And if we exclude this possibility, then in the sense that we can always, like for example, I have A, B, C, D. If I do the same example here, if I have like BB, CBBB or something like that, 001, 01, 01, 01, there's always no ambiguity that like there's only one, each time there's only one possibility. So therefore like, okay, prefix free code, nice, very good. So that's the conclusion. But the question is like, of course this is a subset of uniquely decodable code. So the question is like, is this efficient? Efficient in the sense that if I restrict myself, only consider prefix free code, then my expectation like Lx will be still the same as like if I don't restrict that. Will that like assuming like prefix free code is not an efficient code in the sense, then this value, if I constrain that like only consider code to be prefix free, I may have this thing is bigger than like Lx without the constraint. So this is like forced to be prefix free. Right? So the nice result is that like wait a sec.
Could it be greater than or equal to?
Oh yeah, I guess yeah, yeah, but yes. It can be equal. Greater than equal to, like, it must be, right? Actually, it must be, right? But the thing is, I want to put a question mark, is like, will it be greater?
Okay.
Yeah, because it will always true, like, for greater and equal to.
Yeah.
Yeah. So, actually, I'm going faster than I expected. So therefore, like, I didn't prepare that I need to go back to like 2 years. Let's see, Kraft's inequality. Let's see. Yes, let me talk about Kraft's inequality. So Kraft. So this. Okay, my handwriting is getting worse and worse. So Kraft's inequality is like a condition to track whether like a uniquely decodable code exists. For let's say if I have see. So remember that like if we when we try to construct a code, we always want the expected length to be as small as possible, right? But if the length is getting too small, then like it won't be uniquely decodable anymore. And basically, Kraft's inequality is saying that okay, up to which point that you can have this L to be the size to be how short this L can be until that like uniquely decodable property will be break down. Will break down. So, and let me just write the condition. Basically, it's saying that like if you have k symbol here, like x1 up to xk, and let's say I have like the length of this symbol, let's say it's L1 up to LK. Actually, yeah, I need to be very careful when I talk about this thing here. Let's say I have x symbol x1 up to xk, and let's say I have like k value here, L1 up to LK here. If I satisfy this Kraft's inequality that basically sum over like 2 to the minus LK is less than equal to 1, then I will be able to find a code such that like the length will be just I will have like the length of like oops, suddenly I cannot write. Oh, wait a sec. I guess I can use my finger. Ah, it's okay. Let me keep the. So then I can have like C. Basically the code word like for x1 is cx1, and the length. Let's say I can find a code such that like cx1 with length L1 and cxk with length LK, and such that that code will be uniquely decodable. So be careful, like because as I just mentioned. Okay, let me have some question.
We were just discussing something from your lecture notes.
Yeah. So which part? Maybe like.
The
Oh, I skipped that. Wait. Oh, the diagram like here. This one or?
Yeah, that diagram.
Oh, okay. Yeah. Yes, we Oh, okay. Yeah, where am I? Yes. I mean, I said that like we need to be a little bit careful here. It's like it doesn't mean that like if you have code that satisfy this length condition, it will be automatically uniquely decodable. Of course, it shouldn't be that way, right? But rather, it's just saying that like if you have this length like or like these parameters that satisfy this constraint here or this condition here, then I can find code that actually have this kind of length, and that code will be unique. I mean, just have an existence of that uniquely decodable code. And as you're kind of so basically, let's see, I have forward proof and converse proof. Oh, actually, I only when I state this class inequality here, I only state the forward condition, forward statement. But also, there's a converse statement here. It's basically when this constraint, when this condition is not satisfied, then you cannot find any code with this kind of length parameters. Yeah. So and for the forward, we'll be like, okay, given this length here, how can we argue that such code exists? So we have that diagram here, as you can see here. So basically, what we can do is like, we can just yes. Okay, so Pigeon, you, I mean, reading that diagram also, I figure
Yeah,
out.
you're looking at the diagram.
So honestly, I think like this proof I added that in the last time. Uh, so I think it should be correct, but I'm not. Uh, I should at least high level it should be correct. Maybe like have some minor issue here and there. Um, but the point is like okay, like you try to construct a tree for that way, and you can think of like for each cohort you just put it on the tree as a node on the tree there. Now the yeah, I guess I'll try to let you guys study that a little bit. It's better. So you see the So you got that? Kind of. So you guys get the proof yourself, like, or so I continue with yeah. Okay. Let so for the forward proof, like again, like so what we want is let's do a pen now. So given this L, we want to make sure that we can find such code, right? So the idea is say, okay, given the length L here, so I guess I would just do it by example, something like that. Let's say if I have length L is like 1, 2, 3, 3, something like that. This satisfy the, or like let's not consider whether it's satisfied or not, but let's build a tree, a binary tree, with like the node is actually correspond to the I mean the length okay, the location of the node will be I mean the depth of that node will correspond to the length of that code word. So in the sense like let's say if I have like a binary tree that supposedly I start with like this tick value 0, 1, and then I have like 0, 0, 0, 1, and then maybe 0, 0, 1, 0, 0, oh, sorry, 0, 0, 0, 0, 0, 1, and so on and so forth. Stuff like that, continue the control. Now, what I mean is like if I have a code word of length 1, then I should find a code word in the depth 1 here. So let's say I have pick this one, let's say. And then I have another one like 2. So what I'm going to do is I'm just like for the one I pick, I'll just exclude all the descendant. Let's say like this, I won't pick this anymore. I will look for like stuff in depth 2, then I can pick a node here, let's say, and this is like let's say 1, 0 here. And then I similarly, once I pick this 1, 0, I will kind of exclude everything like for its descendant for what I'm going to pick next. So let's say if I have another simple one to have 3 here, then I will have to say let's say 1, 1. This is a 1, 1, 0, and this is a 1, 1, 1. Let's say I pick this thing here. So what I mean is that eventually for this choice of lanes like 1, 2, 3, 3, I pick this code word here, 0, 1, 0, and 1, 1, 0, and 1, 1, 1. Now this apparently if I can do that, this will be a prefix-free code, right? Of course, one possibility is I will have code word, for example, I have another code word afterward. Let's say instead of 1, 2, 3, 3, I actually have 4 code words. I have 4 here. Let's say now I cannot pick anything, right? Because this also calls out all the descendant here, and I cannot pick anything. Then I won't be kind of able to pick a code. But if my procedure like this is possible, then this I will get result in the prefix-free code. Right? So the only thing I need to prove is that I want to show that whenever the Kraft's inequality condition is satisfied, then I will always able to pick a code like this. With the procedure I just described, I will be able to pick a code, and that code will result in the prefix-free code. And now if I look at what I did here for the Kraft's inequality, so if I look at, I count all the descendants at the level of the longest code word. So let's say in this case it will be 3 here for each of the code. Each of the code word. For example, for this guy here, the number of descendants at level 3 here will be 4, right? Here, because I have 4 of these descendants, 0, 0, 0, 0, 0, 1, 0, 1, 0, and 0, 1, 1 here. And I get this 4 because this should be, this value is just equal to 2 to the minus L1 minus, 2 to L mass minus L1 here, where this L mass is equal to 3. That's how I get 4. Is that, let's see, no, I'm sorry. I have a minus sign here. I should remove this minus sign. That means, oh, right? That's right. So, and similarly, I can do the same thing, right? For this guy here, I have 2 descendants here. That is basically 2. How I got that is basically 2 to the L mass minus this L2 here. So you can see that the procedure is possible as long as I count the deepest level, that the sum of all these descendants has to be less than equal to the number of code words at this level, right? In that case, it would be 2 to the L max, right? So if I can make sure that sum over this 2 to the L max minus L, sum over all, maybe I write Li, sum of all I, satisfy this, then the procedure is possible, right? But this is exactly just equal to this Kraft's inequality, right? Because I have this L mass got cancelled, then it's just sum over 2 to the minus Li is less than equal to 1. And this, is that clear? Kind of, yeah. So therefore we have this, whenever the Kraft's inequality is satisfied, we can always build such code. So therefore, since this is prefix-free, this will be uniquely decodable. Now for the converse, we said that this has also, I didn't actually my slide didn't state the converse in my statement, but the converse would be if this is not satisfied, if this is bigger than 1, then always we cannot find a uniquely decodable code. So let's see. Let me start a new page here. So what we are going to do is I don't know whether I should go to the slides here. I got a little bit tired writing. But I think like typically when we write that like students can follow better. Like that's my experience. Let me just keep writing maybe. So anyway, so let's say we'll consider this is kind of weird, like why we consider this. But let's say I have coding for k symbols, like x1 up to xk here. If I try to code that, and let's say consider the Kraft inequality, the left hand side of the Kraft inequality to the power k. So and this will be kind of equal to sum over x1, let's say 2 to the minus l x1 times x2 x 2 to the minus l x2, and so I have k times here, right? It's kx to the minus l xk. And then of course I can expand that. It will be just equal to sum over this x1 up to xk into this x to the k and 2 to the minus l x l x1 plus l xk. Now, but what's this? It's basically just the length of coding k symbol, right? So it's essentially just equal to 2 to minus lx, right? And this is also like this is sum over all the possible k symbol stream, and I can write it in another way. In the sense that like I can group all the symbol with length m together. So instead of writing the sum like for each of the code word there, I can write it as a sum with like 2 to the minus m. M is equal to from 1 to k l max. So L max is the maximum length there. I have k symbol there, and of course I need to add something here because am here is basically saying that like for length m, for symbols sequence that will code into a length m code word, I will have am of them. So for things to be uniquely decodable, am Oh, okay. Yeah, I'm kind of silly. Yeah, I was thinking like why I need as I wrote here why AM. So of course AM has to be less than 2 to the m, right? Okay, makes sense, right? I mean like again like AM here is like how many input stream that will code into like a length m code word there. And I only have 2 to m so many length m code word. So I need to make sure there will be no conflict like when they map to the this code words there. So therefore I need to make sure that AM is less than the total number of this length m code word. So if that is the case, then therefore like this will be just sum or this will be just cancel, right? This has to be less than equal to, so therefore this will be less than equal to sum over 1 m equal to 1 to KL max. So therefore it's less than equal to KL max, right? Something like. But then like I can have this is like to the power k, right? So I can take like inverse k power like on both hand sides. So I have like eventually I will have like sum over x to the minus lx is less than equal to KL max to the 1 over k. And of course we didn't have any constraint for k here, so we can take k for arbitrary value. So in practice we can take, in theory we can take k to infinity, then in this case this will be just equal to 1, right? So that means that like whenever that things are uniquely decodable, we need to ensure that the crossing inequality has to be satisfied. Therefore the converse is proved. So I guess I probably just stop here, and then I think it's going to cut down this from the experience last time. You just shut it down automatically. So I will send you guys invitation next time, just before class. Also, please check email.